One of the most frustrating and dangerous sources of bad reasoning is not being clear about what you're talking about. And one of the ways that we can sometimes do that is that when we specify a certain number, if I say 17, I think everybody's clear on what I'm talking about. But if I say X, it's not so clear what's going on there. And so we've, over the years as a species, developed a method for being very specific about what it is that we're talking about, and we find it very useful. So what we're going to do is talk about this method and then in the end illustrate it with one of the most important concepts or conceptual tools in computer science that's also used in mathematics that can be expressed much more carefully and in a way that makes things provable than if we just try to hand wave. So we're going to start by illustrating this with quadratics, and let's just jump in with something. I've picked one out because it illustrates a lot of these properties, and so this is just basic algebra. So I've got here x squared plus 4x plus 5, and you know what? That's a meaningless expression. It's an expression. An expression means something that's made up of mathematical symbols and doesn't have any kind of contradiction in it. But it doesn't mean anything. And it doesn't mean anything because we don't know what x is. And so in any time that you're going to talk about something like this, not just a quadratic, but any other kind of logical or computational or mathematical or political expression, you got to make sure that all of the terms are, if not defined, then that you know what the scope for them is. So in computer science, this is often a lot clearer because a lot of languages demand some kind of scope statement, but that's the deal. Anyway, x squared plus 4x plus 5, oh, it's beautiful, doesn't mean anything. So one way that I can change that is I can make that the definition of a function. So if I write f of x is x squared plus 4x plus 5, that now defines for us a function f, and we still aren't a little bit as clear as we should be on what x is, and so we can specify, say, x is a real number. That's not good enough, but that's a good first pass. So now this defines an algorithm, right? We're going to take whatever you give it, we're going to square it, we're going to multiply by 4, we're going to add those up, and then we're going to add 5, and then we'll have a party. So that's one thing that we can do. And now that expression means something because it defines a function. And the function formula is what the function does to x. Okay. There's another thing that we can do, and this is, again, a very common mathematical situation that often leads to computational questions, is I can try to solve the equation x squared plus 4x plus 5 equals 0. So that's now an equation. So let me finish writing that down. That's an equation. An equation is a statement in the sense that we've been using the concept of statement as a sentence that's true or false. This is either true or, well, not yet. We're getting there. But this is a sentence. The verb is equals, and that's what makes it an equation. An equation is a sentence where the verb is equals. So this still doesn't quite, this isn't a statement just yet because we don't know what x is. And so there are two directions that we can go from looking at this. And so that's a nice equation. Implicitly, when we write that, it means, oh, solve for x. But we've got a little bit of a surprise here. If you, the easiest way, I think, to do this is to rewrite that expression, a little bit of algebra. So x squared plus 4x plus 4 is the perfect square x plus 2, and then we've added 1. And what we see here is a square plus 1. This is never 0. So now we have set ourselves, we've actually answered a question. The question is, does there exist an x? Can you solve x squared plus 4x plus 5 equals 0? So the way we write that statement mathematically is to use the existential quantifier. That's the backwards E. And so now I can say this. Let me write it out carefully. So I have written a statement, and it is a genuine statement now. So the statement is, there exists an X with this property. So this is some proposition. And so we've introduced the variable X. Now we know what we're doing. Here we're making, the statement is that the solution exists. This is the statement that a solution exists. And it doesn't. So this is a statement and it's false. But it's still a statement, and so we're happy to accept it as such, because something that is known to be false is still a statement. This one, without the quantifier, is not a statement because we don't know what X is. This is where bad reasoning begins, by not knowing what X is. So there's another direction that we can go with this quadratic, and that is that we happen to notice that when we rewrote it, we got a square plus 1, so that's never 0 and never negative. So let me write a new statement, and this statement says that for every x, x squared plus 4x plus 5 is, oh, I put an extra parentheses in there, sorry, is greater than 0. So sorry about the blob, but so this is the so-called universal quantifier. For every x, x squared plus 4x plus 5 is greater than 0. Now that's a statement again, because we have a very precise idea of the scope of x. And so we're saying, oh, is this true for every x? And in fact, this one is. So this is a statement, and this statement is true. And so statements, that's the thing about a statement. It's either true or false. And so there's another statement. So by using these quantifiers, we change vague stuff into statements, something that's either true or false. Hey, I need to take a little sidebar here, because a couple of people on the midterm defined a statement as something that is provably true or false. That's a very subtle point, and it doesn't have to be provable. It just has to be true or false. So the provability adds another bit of context to this thing that is way beyond the scope of this course. So it's not provable. It's a statement that is true, is a sentence that is true or is false. So here are, let's go back to this. Here are some statements, and they're statements because they have these quantifiers. The backwards E is for every, asserting that there exists such a thing. There may or may not be. You would prove that by constructing it. That's the best way to do that. So in this case, you would prove this statement by solving the quadratic, which you can't do. Oh, well. And at least in the reals. And this statement requires a little bit more proof because it's for every. We can't just pick one. It's for every. And so we're there with that. So we can make other kinds of interesting statements that translate mathematical concepts, computational concepts, physical concepts into actual logical statements. And so let me look at one very, very quickly, and that's this. Let me write it out. One of the things that we're trying not to do is to implicitly make assumptions about what symbols mean. And so that's something, mathematics is strongly typed. You have to define all the terms. You can't just let the compiler figure out, oh, X is real, X is complex, X is absurd, X is whatever. You've got to say. Mathematics is strongly typed. So anyway, so here is a statement here. There exists an X with the property that f of x equals g of x. And I'm a little bit guilty here of not saying what f and g are. By context, you would say, oh, those are functions. Okay. So we've got these two functions, and this is saying that their graphs cross. So depending on the functions, this may or may not be true. So, so this is another way that we can employ these quantifiers. So The other thing that we have to do, and this is a general principle with any kind of reasoning, is if you want to make a statement, you also need to be able to make the negation of that statement. We've already seen that in the De Morgan laws, because that is the negation of and, or the negation of or, and you don't really understand something until you understand its negative. And in fact, you don't really understand implication until you've looked at its negation. And so, how are we going to negate these quantifiers? The quantifiers make a statement, and we want to negate them. So let me start with this statement. There exists an x, and I'm going to be vague about the property that has some property p of x. And that might be something like this. It might be some logical property. It's just saying, oh, there is an x that has that property. And the negation of that is that every x does not have that property. That's a little bit awkward, but that's the way we have to say it. So I'm going to throw in a negation here, and I'm not going to try to do this symbolically. I'm just going to say that this means that for every x, the negation of p is true. So that is not p of x. If you think about this for a second, that makes perfect sense. And so that's the situation. If you're asserting that there is such a thing, then the negation of that is saying for everything it's not true. So there is or there isn't. And so that's the negation of there exists of the existential quantifier. And we can do the same kind of thing with the universal quantifier. So let's say we have some property, for every x, q of x. So we've seen an example of that up here. We've got for every x, this quadratic is greater than 0. So this is the statement that we are now compounding by defining it's really simplifying. Anyway, if we're going to negate this, so I guess I'm being read about negation. What this means, how can it not be the case that every x has the property? Well, that means there's one that doesn't. And so that is the negation of this universal. So there exists an x such that q of x is not true, not q of x. So I've color-coded these a little bit, but those are the negations. And so these are the basic things that we can do with quantifiers. From now on, for the rest of your life, when you introduce a symbol, you either have to say what it means or you have to include a quantifier. Every time you introduce a symbol, if you do not this, what you've said from there on is wrong, it is incorrect. You're talking about something that you haven't specified, and you just can't do that with any level of precision. So you can depend on context to a certain extent. If you're doing algebra and you've got y equals x squared plus 4x plus 5, well, that means every x is on the horizontal axis and y is being determined by x, or so forth and so on. But you need to define every symbol, every symbol, every symbol. And so there's the situation. Okay, so let's finish this up with a very important definition from computer science that we'll see more of a little bit in this course, but then in more advanced courses, you're going to see this a lot. And so what we're going to have here is that f and g are functions, and we'll just have their inputs be natural numbers. So you're putting in 0, 1, 2, 3. When we talk about induction, we'll get more about the natural numbers, but I'm sorry, in computing, it's 0, 1, 2, 3, so forth and so on. In mathematics, it's 1, 2, 3, 4, and so forth and so on. Computing starts with 0, mathematics starts with 1. That's just kind of a social convention. Anyway, so what we want to define is the concept of big O. So F is big O of G. And this means that their growth is similar. And so this is a very common talk or thing that you'll hear when people talk about computing problems and say, well, yeah, that's big O of n log n. That's the most frequent one you'll find. And so So what do they mean by big O of G? And the expression is just full of quantifiers and logical symbols. And so let's write it out and kind of look at what it means. So what we're saying here is there exists an M. I'm not done yet. I'm just pausing. So you're going to have to construct an M or show that somehow that there is such an M. And there exists a C, that's a small c, and so again, you're going to have to construct C. When someone says prove blah 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 exists, construct it. That's the most reliable method. It's not the only method, but it's the most reliable method. And now we're going to write out the property that M, C, F, and G have to have, and you'll see when we're done that everything has been defined, and that every symbol that we've talked about is defined. So there's an implicit definition of it in here, but we'll take that. So what we're going to say is this. We're going to say that if n is bigger than m, that's there's an implicit for every in there. And so sometimes people forget to say that. But this is an implicit for every. Or you can say, well, if n is not bigger than m, that's the irrelevant part of implication. Either way. But anyway, if n is bigger than m, that implies that f of n in absolute value is less than or equal to c times the absolute value of g of n. Kind of crowded in there, sorry. But this is the definition of big O. So this is a very precise way of saying eventually there exists a point such that after that point. So these two together mean eventually. And so that's a trick that you can use to translate statements in language into this precise logical statement. And there exists a C so that the absolute value of F is less than C times the absolute value of G. So eventually we find out that we can control the growth of F if we know the growth of G. So we can say if something is big O of n squared, that means it kind of grows like quadratically. Or if something is exponential, well, the world can't handle that, but that's the deal. So these are the quantifiers. This is a very important way in which they're used, and we'll continue to use them. And this is a serious rule. You've been initiated into a secret society so that for the rest of your life you will never introduce a symbol without either defining it strictly, X is for, or putting a scope on it. There exists an X, or for every X, or for every X with a certain property, or so forth and so on. You've got to do it. This will cost you points, dollars, bridges falling down. You've got to define all the symbols that you use.